Yeah, so good morning everyone. Welcome to our session. Please come to stage. Yeah, my name is Alexander Kukushkin. I work as a principal engineer at Microsoft. Like about 10 years ago, and specifically on 8th of July, Patroni got its name. And I'm the main contributor and developer and maintainer of Patroni project. And my co-presenter, Polina.
Yeah, my name is Polina. I work at Zalando, which is probably not known here, but this is an e-commerce fashion platform from Europe. And I'm a smaller maintainer of Patroni project. And I will help Alexander to describe how Patroni works in the very short words, how it works and why it works the way it works. Okay, so we will have the following agenda today. First, we will talk about shortly, like what it is really, very shortly, what are the main functions. Then we will discuss what are the main approaches to do high availability, automatic failover, and what are the common ways, why are they probably wrong, and what is done in Patroni specifically, and why Patroni has the architecture it has. And then we will go deeper into Patroni. We'll try to have a quick overview of what it is inside and what are the main functions. So probably you will be able to understand a bit better what is behind and how maybe what are the principles behind Patroni.
All right. So what Patroni is really? Yeah, first of all, Patroni originated as a governor project, which was originally created by Compose company. Nowadays, Compose is a part of IBM, and I think they use Patroni to run database as a service on Kubernetes, like in the IBM cloud. At least it used to be like a few years back. I'm not sure about like current state, but people who worked back then like explained me all details how they run HA Postgres. Right. So back at Zalando, we started contributing to Governor without very much success because they did not really accept our pull request, but we had a lot of great ideas like how to improve original project and did a lot of work in our public fork, which was hosted in Zalando GitHub organization. Later, when the number of changes that we accumulated got very critical, we thought about really forking it and giving it a different name. So how Patroni was created. So what it does, first of all, the main feature of Patroni and what it is supposed to do, it's automatic failover, and I think it does it pretty well. Of course, in the life cycle of every system, you need to first of all create a new cluster, highly available cluster. You need to initialize primary, you need to initialize standbys, and only after that you do automatic failover. Of course, Patroni also automated this part as well. Besides that, when you run your cluster, at one point you need to change configuration, and preferably you better apply the same configuration on all nodes in the cluster. And Patroni got a feature of managing configuration, Postgres configuration parameters. And it's very important actually to keep configuration parameters, some configuration parameters the same on all nodes. Because for instance, max connections cannot be set to lower value on the standby than on the primary. That's why Patroni is implementing some tricks here and there. And of course, Patroni helps to monitor your HA cluster. It's not like full-blown replacement of your monitoring solution. You better have something deployed specifically to monitor health of your Postgres. But Patroni gives you some ideas about state of Postgres, and like you can use Patroni REST API to like plug into your monitoring system and to see like whether your HA is working, like not working, like where the primary is, and so on. All right, so now Polina will hopefully explain how not to do HA. You can use this mic.
Okay, so it's a bit. I will handle this. Okay. So when we think about how to build our highly available system for Postgres for your setup, the first thing that comes into your mind is just to have a very simple setup of two nodes, one of which is primary, the second is standby, which is replicating using wall stream from the primary. And then you would probably think that you can establish a health check connection from standby to primary to periodically check if your primary is still alive, and do something in case you do not see it anymore. If in case standby doesn't see it anymore, it will do something to promote itself. But there is a problem in this scheme. Let's consider something happened not with the primary, but with the network itself. So primary is still running, but the network is not working, and standby cannot reach primary. In this case, for the standby, from the perspective of the standby, it seems that primary is down, is dead, and it needs to promote. But in fact, it's not the case. And this leads to the very worst situation for every DBA, split brain, when two primaries are running simultaneously. So it seems this is not the best solution we can use to build our highly available system for Postgres. The next step to solve this problem, we would probably think that we need to do something before promoting. We apparently need to do something with primary to make sure it's not running. So when we promote, we have only one primary running. For that, you can use different approaches. But to sum up, you probably want to perform the stonith, which is the shoot the other node in the head approach. Basically, you make sure the old primary is not running when you are about to promote, if you are standby. And to reliably do this, you will need the secondary network, backup network, recovery network. And this already looks better, and we think that we can manage like this. But unfortunately, in real life, it's almost impossible to implement correctly. There are a lot of corner cases which you will not cover. So apparently we can do better. Next approach, which is very popular nowadays, in very big projects, by the way, which are gaining some popularity now, but the approach is to have a witness node that will be an arbiter, some call it arbiter, that will look into all our Postgres nodes and perform health check from it, so that it's not standby querying primary, but this witness node. Already looks better. But if something happens with this node, it of course becomes the single point of failure. And yeah, that's probably also not the best we can do. And another problem with this approach, this was the easiest problem, but actually there is another problem with this. Again, if we think about the network problem, in this case it's a so-called network split, when our witness node suddenly cannot see primary, but it cannot see standby. If it's again the same problem as we discussed before, we cannot make sure primary is actually dead, because it might be that it's just not reachable. And we again need a secondary network to make sure we shut it down, we kill it before promoting the standby. This way, we are returning to the first problem I described. We are having split brain very easily in this scheme. So, to sum up, what are the main points you need to look into when you are building your high availability solution for your Postgres cluster? The main problem is network partition. It's the most complicated problem, and you always need to consider how it could happen, what will you do in this case, and also not try to think of more sophisticated schemas of network partitioning, because there are actually a lot of different possibilities for it to break. Also think about the possible split brain. You need to perform so-called fencing. Again, you need to make sure that your primary that was running before actually not running, so that you do not get the standby that you are about to promote running in parallel with the old primary. You can use, I already described the Stonith approach. It can be implemented in many ways. You can, for example, just perform it on the low level. For example, just switch down the electricity. And this way you make sure this instance is not running and Postgres is not running on the old primary. You can also configure some proxy in front of your Postgres instances that are routing your user queries to your instances. And in case of failover, you can just reconfigure the proxy. And you do not need to kill primary, you just reconfigure the proxy. However, this is not perfect in all the cases, because you can still have some local connections to the Postgres, which are not going through the primary. For example, pgcron. Probably some of you have used this. And those queries will still run. And yeah, it becomes even more complicated if we're speaking about Kubernetes. So this is also not perfect. This way, our approach and like from our point of view, the most effective way to fence your primary is to perform self-fencing when you do something locally. So there is something that performs Stonith near your old primary that makes sure that it's not running anymore. And the third thing that I have not talked about yet, but this is also important, that it may be possible that something happens with the system where your primary is running. It's not about like Postgres itself, but maybe there is a resource starvation or whatever happens with the system, the whole machine, for example. In this case, you need to switch it down, reboot it, and to make sure that everything is working again. For this, there is an approach that is called watchdog. So these are the main points that we consider, and yeah, I would say everyone consider the most important in the high availability. So, okay. As I said, local fencing. This means that we need some kind of agent running near Postgres. So on each node where you have Postgres running, you place an agent that is watching for your Postgres instance. And there is also a witness node, an arbiter that we have spoken before. So, like, this seems to implement everything that we have just talked about, all the main points. Still, there is a problem actually in this scheme. Let's think about multi-data center deployment, or if we are speaking about cloud deployments of different availability zones. In this case, there might be a situation when your witness node is located in the same data center or availability zone with your primary currently running, and something happens with the network from this data center to all others. And you can also not reach it from outside, for example. But the most important is that your standbys cannot reach primary. In this case, from the perspective of witness node, everything is fine. It can see the primary, and it can talk to it. So we lost some standbys, but it's still, we still from its perspective can perform writes. But in fact, it's not the truth, because from the outside, you cannot reach it. And we have 2 healthy instances running now, but the witness node cannot do anything about that. It cannot perform failover, because from its perspective, they are dead, but primary is alive. Finally, thinking of all those problems, how to do it right. It seems that we need to implement some kind of collaborative decision, or so-called quorum-based decision that all the components will do together to ensure that we perform a failover with the most efficient way, and we are aware of the state of all the components in the system. And this now starting to remind you of something if you have already worked with Patroni. Yeah, just to be more precise, this this algorithm can be implemented manually, but of course, probably you have already something that is implementing it from the outside. For example, you have a console or etcd. And why to implement something from scratch if you already have such a system that implements the quorum algorithm? For example, etcd. Then it becomes the external quorum, and the agents are near the Postgres instances. And this, if you're already using Patroni, starts to remind you of something. This is how Patroni actually works.
Still, this mic doesn't work, so I will continue with this one. All right, so how actually Patroni works? The general idea, we need to use some external distributed key value store or distributed configuration store, as we call it, because like Patroni keeps its own configuration and metadata inside it. Example of such configuration stores are etcd, console, zookeeper, or like Kubernetes control plane, which is in fact just API on top of etcd. It has to implement some consensus protocol. For example, Raft in case of console and etcd, or ZAP instead of zookeeper. Of course, it needs to provide interface of key value store, so we need to be able to read and write keys to such system. It's important that such system has like API of compare and swap or compare and set, because we want to update keys conditionally. Like let's say we want to update leader key in case if it's current index or current value stored in this key matches a certain value which we know. Nice to have, but not really required. It's ability to expire data based on TTL or lease or session, and ability to watch for changes on certain keys or all keys like we want. So how Patroni like uses such distributed key value store? The leader, the primary, periodically updates a leader key in etcd, like in this example, and in the future on all slides I'm going to use etcd as an example because it's less confusing and more simple for everyone. And in this specific case we are still relying on the old version 2 API because it's again easier to explain. Leader periodically updates its key, puts its name into a value of the leader key and sets TTL to 30 seconds. In case if leader key isn't updated for 30 seconds, it will expire. That's a property that etcd provides. At the same time, leader also updates a whole bunch of other keys, like not necessarily every cycle of its lifetime, but it updates status key. It also updates like member key that represents its node and maybe some other keys like conditionally. All other nodes just updating their member key because they also have TTL in order to detect that some clusters are gone, some members are gone from the cluster. And all standby nodes are watching for the leader key. So they want to get notification if leader key expired. So it's not a leader race, but whatever. So normally primary is continue to running as a primary in case if it managed to successfully update its leader key. And this update is done conditionally. That's also very important. We are specifying that I would like to update a leader key with the value A because it's node A, and the current value of the leader key must also be A. So in case if someone else already managed to require leader lock, we don't we want to be able to detect such situation, and etcd API allows us to do it using compare and swap operation. And in case if leader key was successfully updated, Patroni will continue operating Postgres normally, and Postgres will be running the primary. At the same time, standby nodes just updating their members key and watching for the leader. In case if primary is down, leader key expires. On this slide we have TTL 1 second, and in 1 second leader key is expired. Standby nodes will get a notification that leader key is absent in the etcd. It's gone. It means that we got no leader. This is how Patroni detects failure of the primary. And when there is no leader key, it triggers a leader race. It's not a leader election, in fact. It's really a race, because every node races with any other node in the cluster. So but every node needs to know whether it's the most up to date. It managed to receive and replay the most of write ahead lock. Comparing to other nodes. How Patroni does it? For that, Patroni is relying on its own REST API, and every standby calls REST API of any other standby node to get wall position up to which node managed to receive write ahead lock. What's also important, they also call previously known primary, because they really want to make sure that it's not responding to REST API requests. So why it's important? Because let's say primary is still running, but it just lost access to etcd, and it did not manage to demote for some reason. We want to be able to detect such situations, therefore we also call the formerly known primary. In this example, we get request timeout from the old primary, on both nodes, and both standby nodes are on the same wall position, 100, just arbitrary number. Since they both qualify to be new primary, they start creating of the leader key in etcd. But again, here we rely on compare and swap operation. We specify pref exist equal false. It means request to etcd should succeed only when there is no leader key existing in the etcd. And it means that only one of such requests will succeed. The second one is guaranteed to fail, because the first one already created a key, and the second one will, so etcd will notice the key already exists, because every write is linearizable, I'm sorry, and fail. So, and once one of the node managed to successfully create leader key, it will promote standby to the primary. So like in this case, it's node B. And node C will get information about new leader from etcd, update its recovery conf or like primary conf and start replicating from the new leader. What will happen in case of node A, like which was a leader, fails to update its leader key because the whole network is partitioned. Property of etcd is that write only succeeds to the etcd only when it is able to replicate this write to majority of the node. If one of the nodes is isolated, it will not be able to send requests to remaining nodes, and therefore such write will fail. And primary will fail to update its leader key. And if it failed to update its leader key, Postgres will be demoted to read-only. So Patroni just literally performs immediate shutdown of Postgres and starts Postgres in recovery, like in read-only mode. But the rest of nodes in etcd cluster will continue to operate normally. Like it will be writable. And the standby node will detect that leader key is expiring, and when it is expired, it will get notification about expiration. It will again trigger a leader race, and standby will be promoted. But what's important, at the moment when standby is being promoted, primary, the old primary, already demoted itself. So we don't have a split brain situation. So, and this is like how we try to represent the one heartbeat which Patroni like periodically runs. Like every heartbeat is executed every loop wait seconds. Like loop wait is a configuration parameter of Patroni. By default, it's 10 seconds. And every heartbeat, Patroni, like on every node, executes get cluster operation. So it gets the state of the entire cluster from etcd. But in case if one of etcd node fails, we want to be resilient, and therefore, like when such request fails, we switch to another node and retry. And in total, Patroni can spend up to retry timeout, like performing such get cluster request. Once Patroni managed to get cluster state from etcd, on the leader node, we need to update leader. And since like our priority to always have a primary like in the cluster, we also retry such update leader requests. Like for instance, like get cluster managed to succeed, but update leader failed because like something happened with etcd node where we connected to. Patroni switches to another node and again retries request. Like in case of second node of etcd also like not working properly, like it continues with the next one until retry timeout time is exhausted. And besides that, on the primary, Patroni updates its status key, like of the entire cluster, where it keeps some cluster state information. Maybe updates failover key, maybe updates state of synchronous replication, and so on. However, like you maybe have seen in the Patroni documentation this very important rule. Like the value of TTL should not exceed the total value of loop wait plus 2 times retry timeout. Loop wait, it's time Patroni sleeps between 2 heartbeat cycles. TTL, it's for how, so effectively how fast Patroni can detect the failure of the primary. Like after TTL, the leader key expires and we can detect it. And 2 retry timeouts, like the most interesting one, it's like this magical value 2. Like, and it's not magical, it's because primary has to do get cluster, and let's imagine that get cluster was failing, and at the very last millisecond it managed to succeed. So Patroni does not demote primary. And after that, Patroni starts updating leader key. And we cannot infinitely retry such update leader key operation, and we need to stop before TTL expires. That's why, like, we have to retry timeouts. So, yeah. Now let's look at what is stored inside DCS. And
yeah, let's quickly look at what is this magical data written to the distributed configuration store DCS. There is an ultimate list of what can be written to your distributed configuration store when Patroni is using it. In the bold, you can see that what is always written. So it is configuration. It's a global configuration that is applied to all the instances. It's very handy that you can just configure it in one place and it will be distributed to all the instances of your cluster. We also call it dynamic configuration. Then there is an initialize key, which is just unique identifier of this cluster. Then the most important key is the leader key. It's just the name of the current primary, the current leader of the cluster. This is the node name, which is stored under this key. Then we have members, all the members, as we previously said. Leader key is written by leader, and all other keys, by the way, but the member key is written by all other nodes, the standby nodes. They update their information about themselves. This way, you can also use this as a discovery, like a service discovery, for example, to get information how to connect to this instance. Yeah, so also the status key, which stores some important information about the current state of the cluster. We will look into this a bit later. And some other you might know. History is the history of all the failovers and switchovers. Failover is the currently performed failover switchover with all the information, and synchronous node is written in case you are using synchronous replication. Okay, so if you are using Patroni, I hope some of you use it. You probably know this table and this utility, Patroni CTL. When you perform list, you get this table that represents the current state of the cluster. And yeah, I'm just think it will be handy to compare and understand what is actually this data and where it's got from. Sorry, because it's all retrieved from the DCS, from the keys that I have just described. For example, the primary, the current primary, it's identified in this table. It's again, as I said, stored under the leader key. Initialize is the unique identifier. You can see it, oops, here. So this is the unique identifier. This is the current leader. Then we have the members configuration as information. As I said, there is an information about each standby. Again, connection URL, API URL for Patroni, current state of this instance, its role, Patroni version, current location of this member. It's a bit tricky which location it is because we know there are quite some different LSNs you can get from Postgres. But here is the rule how it's defined. The replication state what it is doing with in regards with the primary, because it can stream, but if something is wrong with the replication connection and you have configured archival recovery, there will be an archive recovery state and the current timeline of this instance. Another very important key, as I already said, the status key. The most important value here is the uptime. Uptime is the current flash LSN on the primary. So it's like the ultimate truth for our cluster, what position it is in. Slots, both physical and logical slots, if you configure them for Patroni to maintain. with the name of the slot and the current position. There will also be the member slot, because Patroni also maintains the member slots of all the instances. And the latest feature we have, retain slots. This is a new feature that we added recently. Based on the member slots TTL configuration, there are the slots that are listed here. They will be maintained for TTL seconds after the member disappears from the DCS. For example, it went away, and especially if you do not configure archival recovery, it will help you to keep some walls before this instance. For example, you manually bring it back, so that it can continue to replicate from the primary, because you kept all the necessary walls, because the slot is still there. Yeah, but it's also important to maintain your logical slots state, so that they are in valid state, because you also need to have physical replication slot for that. Okay, and the last, the configuration, also important. As I said, it's distributed. It's for all instances, all the members, where you can see the Patroni configuration that Alex just described, the maximum lag on failover. This is the maximum delay for the replica that is possible for it to be considered as healthy, for the cluster race to become the primary. Also, you can configure PostgreSQL parameters, so that it will be distributed to all the members. Yeah, and some other self-explanatory stuff. Okay.
All right, so what else? Patroni implements a lot of different features. Recently, there weren't so many new features, but last release was quite a big one. And if we talk about some notable features, one of them is a standby cluster, which is allowed to run to utilize Postgres cascading replication to run standby nodes in a different data center and have only one replication connection between them. Synchronous mode, including quorum-based failover. In this case, Patroni is managing synchronous standby names for you by adding or removing some synchronous standbys and fulfilling the replication factors that you specified in the Patroni configuration. And with quorum-based failover, it's also nice that it allows you to reduce write latency and compensate round trip, increased round trip between nodes, comparing to just old synchronous mode. Since version 3, we got DCS failsafe mode, and the reason for it, we got quite a sufficient number of complaints why Patroni is demoting primary while all etcd cluster isn't operating normally. When etcd is fully down, Patroni was apparently demoting primary, and with failsafe mode, it's able to continue to operate in case if primary can see all remaining standby nodes. It's not enabled automatically, you have to do it. Maybe we will revisit it in a future version and enable it automatically for everyone. Although there are corner cases where it may bring some surprises. And last but not least, it's support of Citus. Patroni can manage the full Citus cluster for you, when you add more Citus worker nodes, Patroni will discover them and reconfigure Citus metadata to support it. We collected a whole bunch of useful links about Patroni, and it includes some Postgres FM podcast, which was recorded somewhere in October last year. There is Patroni tutorial from 2018 or 2019. Seems to be a bit outdated. It's very weirdly translated from Russian to English, but and available on YouTube. But I think it is still very good and explains a lot how Patroni works and gives a lot of details and hands-on. I did a whole bunch of talks like step-by-step Patroni cooking guide, which also might be useful, and you may learn some tricks about running Patroni in production. Yeah. Besides that, please read documentation. It has a lot of details, maybe not very nicely organized. By the way, like if you want to contribute to Patroni, like the updating documentation is a very simple task, and you may start from it. Like, and every contribution is very valuable. Please read changelog before reporting bugs. It's very often that happens. Like people report bugs on some very outdated version, which was released 1 or like 2 years ago, but in fact this bug was fixed a long time ago, and changelog describes it. And please subscribe to Patroni Slack channel. Like if you have questions, better to ask them on Slack instead of opening an issue, because on Slack there are many people from Patroni community are active and answering questions promptly, like even faster than I can do. Yeah, that was it. Thank you for listening, and if you have questions, please ask.